Here's an example of doing a calculation with Stokes' theorem. We might be asked to calculate the line integral of this vector field, f of x, y, z is equal to cos x, comma z to the fourth, around the path that moves in straight lines from 0, 0, 1 to 0, 2, 1 to 1, 2, 1 to 1, 0, 1 to 0, 0, 1 back again. So 4 straight lines. If we were going to calculate this normally, then we would be doing 4 line integrals, one for each boundary of this kind of rectangle that's hovering inside inside this two-dimensional plane above the xy plane. But we can observe that in this case, because this curve is closed, it starts and ends at the same place, it ends up being the boundary of a rectangle. And that rectangle is this one, where it's at z is equal to 1, and the x coordinates go between 0 and 1, and the y coordinates go between 0 and 2. So Stokes says we can calculate a double integral of curl of our vector field over this rectangle instead of calculating these 4 line integrals individually. It's not always clear at the outset whether this is going to be better or not. We are going to be doing a double integral, but we're not going to be doing 4 line integrals, and maybe things will simplify. So let's see what happens. The first thing we have to do is we have to calculate the curl of this vector field. We take a grad across this vector field f. And when we write this down, we get I times the y derivative of z to the fourth minus the z derivative of x, that's 0. We get minus j times the z derivative of cos x minus the x derivative of z to the fourth, that's 0. And then plus k times the x derivative of x minus the y derivative of cos x, that's 1. So when we took curl, this particular vector field got a lot simpler. It turned into a constant vector field. Now, to calculate the surface integral, we write down the parameterization of this rectangle. It's all those points whose z coordinate equal to 1, with x between 0 and 1, and y between 0 and 2. We calculate our tangent vectors by taking the u and v derivative. In this case, they're not so bad. We calculate their cross product, which is not so bad. The cross product is 0, 0, 1. Then we evaluate what's our vector field at this point crossed with tu cross tv. Our vector field was 0, 0, 1, and our tangent vector cross product was 0, 0, 1. And so we're going to be integrating 1. So our surface integral is the integral from 0 to 2 of the integral from 0 to 1 of 1 du dv. And so that gives us 2. But then we have to check orientation at the end of the day to make sure that we didn't screw up the orientation. If they matched orientation, then the line integral is going to be 2. And if they don't match, the line integral is going to be minus 2. In this case, we're walking in this direction around the outside boundary, going from point to point to point. And our normal that we calculated, tu cross tv, was the vector 0, 0, 1. And so in this case, we can check that these don't match up. If we try to put our hand with our index finger pointing along the curve and our thumb pointing towards the normal vector, our middle finger wants to stick outside rather than inside the surface. And so these don't match. And so the line integral would actually have been minus 2, which you can go back and you can verify for yourself by checking the calculation of the original 4 line integrals instead.